Okay, so what we're going to do here is we're going to start looking at situations where we have an object on an inclined surface. And let's assume that there is friction. So let's say with friction. Now, if there's no friction, we can easily take it out, but I think it's easier to talk about it with friction and take it away. Okay, so if we have an object on an inclined surface like this and it starts up at the top, we release it, maybe it slides down to the bottom. If there's lots of static friction, then maybe it wouldn't slide down the surface at all. But let's make the assumption that it's going to slide down the surface and there's friction acting on it. So if we think about the forces that would be acting on this object as it is released, we would have the force of gravity. And I'm going to draw the vector for weight pretty long in this picture, and it'll be evident as to why in a few minutes, but I'm going to make that arrow extra long. The normal force is going to be acting as well, but the normal force is going to be up at an angle so that it's perpendicular to the surface, because normal force is always a perpendicular force. And then we have the force of friction. If it's sliding down the surface, then the force of friction is going to be in this direction. So these are our three forces. All right, so analyzing this sort of situation, there's one kind of, I don't want to say trick, but it kind of is a trick for analyzing it in the most easy way possible. And that is, we want to get away from looking at the situation and calling the x direction this way and calling the y direction this way. And the reason I don't want to do that is because the object's not going to be able to move like that. It's going to move in both directions if we use those axes. So I don't want to do it that way. Instead, what I want to do is I want to rotate the coordinate system so that it matches the incline. So now the x direction is along the inclined plane, and the y direction is up off the surface of the incline. This way, now the block only moves in the x direction as I've defined it. That's going to make the problem a little bit easier. So in class I talk about, basically looking at the problem as if you're tilting your head to the side. That's basically what you're doing. All right, so what I'm going to need to do then is I'm going to need to break the weight force, mg, into components, because it's the only force that doesn't match one of these axes. If you look, the normal force is in the positive y direction, and the frictional force is in the negative x direction, but the weight is in between. So I'm going to split the weight up into components. First I'll talk about how to draw it, and then I'll explain what it means. So we have a force this way. That's one of the components, and the other component is parallel to the surface. That's going to make a right angle here, and the angle of the incline, theta, is going to show up right there. It's the same angle. You could prove it using geometry. Okay, but look at this triangle. It's kind of interesting. So the hypotenuse of the triangle is the weight, mg, and the angle is at the top there. So that means that the force at the bottom here is actually mg sine of theta, because that is the opposite side to this triangle. And this side that's coming down is actually mg cosine of theta, because it's the side that's adjacent to the angle. So that's how I split it up into components. And here's how I think about it. Gravity always wants to pull something straight downwards, but the object is not able to move downwards or upwards in this configuration. It's on the slope. So what we do is we imagine that gravity has two jobs. One of its jobs is to make the object slide down the incline. That's this mg sine theta. And the other job that gravity has is to keep the object on the surface of the incline. That's this mg cosine theta force. So those are the two forces that we imagine gravity as having in this scenario. All right, we've broken the forces up into components. Now we write out Newton's second law. And I'm going to do the y equation first. So I write ma in the y direction is equal to the net force acting in the y direction. Okay, now in the y direction, I have the normal force in the positive direction. And I have this mg cosine theta in the negative y direction. And if you think about it, if the block slides down the plane or up the plane, regardless of what its motion on the plane, it has no motion in the y direction. It doesn't come up off the surface or down through it. So the y acceleration is 0. And then I can solve this for n. I get this. Now I don't have a number because I didn't give you a mass to start with. But I think it's useful to just look at it this way. We know that mg is the weight of the object. And cosine of theta is a fraction. In fact, let me draw this. If you know anything about trigonometry, we know that cosine of x, if we draw it as a function of x, kind of looks like this. So it starts at 1, and it ends at 1, and it goes down like this and back up. And if we look at the angles, this is a 90-degree angle. This is 180 degrees. 180. This is 270. And 360. And we could talk about it in radians, but I'm not going to do that for now. Here's the point. Our incline is somewhere between 0 and 90 degrees. Take a look at the cosine. The cosine function drops down towards 0 as the angle approaches 90 degrees. So what this expression for the normal force is saying is that the normal force is the weight times some fraction that depends on the angle. And the bigger the angle is, the less it is. If you think about it, that makes perfect sense. If we make the surface flat, the surface would support the full weight of the object. And if we make the object completely vertical, there would be no normal force. It wouldn't support the object at all. So anywhere in between, at some angle, we're going to get a normal force that is a fraction of the weight. And that's what that says. Now, let's look at the x direction. In the x direction, I have this mg sine theta. That's trying to pull it down the surface, down the slope. And I have the frictional force. So if we think about it, the acceleration is going to depend on this mg sine theta. And again, let me draw this time sine of x as a function of x. If you remember what sine looks like, it starts at 0 and goes like this. And this is 0 degrees, this is 90 degrees, this is 180 degrees, this is 270, this is 360. So for angles between 0 and 90 degrees, the sine of the angle grows. So that means that force is going to grow, and the acceleration will get bigger. Okay, so if we're given the frictional force directly, we could plug that in, and we could solve this for perhaps the acceleration. Many times, however, we're not given the force of friction. What we're given is the coefficient of friction. So if that's the case, we have to remember the relationship between the frictional force and the coefficient of friction. We have to remember that force of friction equals mu times n. So I'm going to make that substitution in here. So then this is going to look like this. And then I'm going to make another substitution. We just determined a few steps ago that the normal force equals mg cosine theta. So I'm going to substitute that in here. And I'm going to get this. Okay, now, you'll notice that in all three terms of this expression, the mass is in there. So I could cancel out the mass. I could divide both sides by m. In fact, the acceleration of an object down an incline does not depend on its mass, because a more massive object is going to have a stronger pull from gravity, but also a larger inertia and a larger friction, and they kind of balance each other out. Okay. So our acceleration is this. And if you look at that, it makes sense, because as the angle of the slope gets bigger, this first term is going to get larger because sine theta grows with the angle. And the second term is going to shrink because cosine of theta shrinks when the angle goes from 0 to 90. So it says that the acceleration grows as we go from 0 to 90 degrees, which would make sense to you if you think about it. The acceleration also depends on the coefficient of friction. If the surface is rougher, the acceleration is going to be less because we have a more negative term in this second term. So if you think about it physically, the example really does make sense. The math is a little different and a little new, but with a little bit of work we can get it.